A customer clicks buy, and 5 things have to happen in order: verify identity, check stock, charge the card, kick off fulfillment, send the confirmation. Charge that card twice and you have a very angry customer. So how do you wire 5 services together with retries without writing fragile glue code? Stack lessons here, picking up right where that thought left off. By the end of this video, you'll know exactly when to reach for API Gateway, when to reach for Step Functions, and how to pick between them and the queues and topics we've already covered. These 2 services are the front door and the project manager of a serverless architecture. In the last episode, we rescued MegaCorp's procurement API by decoupling it with 3 services. Quick refresher: SQS buffers work point-to-point, SNS fans one message out to many subscribers, and EventBridge routes events by their content. And a couple of episodes back, Cognito user pools handed our end users the signed tokens they log in with. Now we add the last 2 pieces: the managed front door for APIs and a way to sequence multi-step work reliably. 5 terms anchor everything we cover today. Let's run through them quickly. Amazon API Gateway is the managed front door for your APIs, handling authorization, throttling, and caching before a single request reaches your backend code. Amazon Web Services Step Functions is the orchestration layer that ties multiple services into one reliable visual workflow. That workflow definition has a name: a state machine, a sequence of named steps with branching logic and built-in error handling. Within Step Functions, you choose between standard and express workflows, and the right choice depends almost entirely on the 5th term: idempotent. An idempotent operation gives the same result no matter how many times it runs, so a duplicate execution does no harm. That property is what unlocks express workflows for high-volume processing. Here's the whole episode in one slide. Each of these 2 services has a crisp job and a keyword that triggers it. When a scenario says expose a serverless API, that's API Gateway, the managed HTTP front door that handles authorization, throttling, and caching, 1 request in, 1 response out. When a scenario says coordinate a multi-step workflow with retries, that's Step Functions, the orchestrator that sequences steps, retries failures, catches errors, and runs branches in parallel. Lock those 2 trigger phrases in, and the right service choice follows directly from the requirement. Amazon Web Services calls API Gateway the front door. And that's not marketing. It's the exact word in the developer guide. Every HTTP request from a client hits API Gateway first, before any of your business logic runs. It's fully managed, so you're not running a fleet of proxy servers to accept traffic. It creates, publishes, secures, and monitors your APIs at any scale. Hold on to that front door image, because it explains everything this service does. Picture the reception desk in MegaCorp's lobby. Every visitor passes the receptionist first. She checks your credentials, confirms you actually have an appointment, and points you to the right floor. What she never does is the actual work upstairs. That's API Gateway exactly. It controls access, enforces traffic limits, and routes you to the correct backend. But the real logic runs somewhere else entirely. Let's trace the path. On the left, a client, a mobile app, or a browser sends an HTTP request. That request lands on API Gateway in the middle, and this is where the front door work happens. It authorizes the caller, applies throttling, optionally serves a cache response, and routes the request. Only then does it flow to the right, to a Lambda function, or a microservice that runs the actual business logic. The gateway sits between the outside world and your code, doing everything except the work itself. API Gateway gives you 2 RESTful products, and choosing between them is a common scenario decision. The REST API is the full-featured one. It gives you per-client throttling, usage plans, API keys, Amazon Web Services web application firewall integration, response caching, and private endpoints. The HTTP API is the lighter, cheaper option, optimized for simply proxying to Lambda with lower latency but none of those advanced features. So the rule is straightforward. If the scenario needs usage plans, per client throttling, web application firewall, or caching, choose the REST API. If it just needs a cheap, simple front door, choose the HTTP API. Throttling is how API Gateway shields your backend from a traffic spike. It uses a token bucket, a steady state rate plus a burst allowance on top. By default, at the account level, that's 10,000 requests per second steady state, with a burst of 5,000 concurrent requests in most regions. Some newer regions default to 1,250. When callers drain the bucket faster than it refills, they get back a 429 too many requests error instead of hammering your Lambda functions. And on REST APIs, you can layer in stage level and method level overrides for finer control. One caution, these are best effort limits, not a hard security wall, so don't lean on them as your cost or security control. Think of caching like an FAQ board in the lobby. When 200 customers ask the same question, the receptionist points at the board instead of calling the warehouse 200 times. API Gateway does the same. It serves repeated identical requests straight from cache for the time to live window, cutting backend calls and latency. The default time to live is 300 seconds. The maximum is 1 hour. And here's the detail that shows up. Caching is a REST API feature only. HTTP is don't support it. It's also billed hourly and not free tier eligible, so don't leave it on in a dev environment. API Gateway gives you a few ways to control access, and matching the scenario to the right one is worth knowing. First, IAM authorization. The caller signs the request with SIG-v4. That's your answer for machine-to-machine calls or Amazon Web Services service calls. Second, a SQL authorizer, where the client passes the JWT token from a Cognito user pool. That's your answer for end-user sign-in, exactly the tokens we set up a few episodes back. Third, a Lambda authorizer, a custom function that validates a token and returns a policy, when your token logic is bespoke. And the fourth item on screen, API keys with usage plans, identifies clients and enforces throttling only. That is deliberately not a security mechanism, and that distinction matters a lot. This one is Amazon Web Services' own explicit warning, not my interpretation. Do not use API keys for authentication or authorization. An API key is like a lobby pass. It identifies which client is calling and lets you meter their traffic, but it says nothing about whether that caller is who they claim to be. If a scenario asks you to actually control who gets in, the answer is an IAM role, a Lambda authorizer, or a Cognito user pool. Anyone who picks API keys for security has walked into the distractor. Let's lock in the front door before we move on. API Gateway is the managed synchronous entry point for your HTTP APIs. The REST API gives you the full feature set. The HTTP API is cheaper and simpler. Throttling shields your backends from spikes, and caching, REST API only, cuts both latency and cost. And real authentication comes from IAM, Cognito, or a Lambda authorizer, never from API keys alone. That's the front door. Now let's look at what happens once a request needs more than one step of work. Here's the pain step functions was built to kill. Without it, teams chain Lambda functions together. Each function calls the next, handcodes its own retry logic, and scatters state across DynamoDB to remember where it was. It works until it doesn't, and then it's brittle, expensive, and miserable to debug. Amazon Web Services even calls Lambda orchestrating Lambda an anti-pattern. On the right is the alternative, a step function state machine. The visual workflow defines the sequence. Retry and catch are built in. The execution state is managed for you, and the whole run is durable and auditable. The coordination logic moves out of your code and into the workflow. Here's step functions in one sentence. It's a serverless state machine that coordinates multiple services into a reliable workflow with retries, error handling, and branches built right in. You define the steps declaratively, and step functions runs them, tracks where each execution is, and handles the failures for you. That's the whole idea. You describe the flow, and it becomes the durable, coordinating layer you'd otherwise have to write and maintain yourself. Think of an airport operations control center. The pilot doesn't personally chase down the refueling truck, the catering, and the ground crew. That would be chaos. Operations control sequences every step on a visual status board. If the catering truck is delayed, control automatically dispatches another one, that's retry. And if the runway suddenly closes, control catches the problem and diverts to a fallback procedure, that's catch. Step functions is that control center for your services. It coordinates everything without doing the physical work itself, and it retries or reroutes when a step goes wrong. A workflow is built from a handful of state types. The workhorse is the task state. It performs actual work by calling a service, like Lambda, DynamoDB, and more than 200 others. A choice state gives you conditional branching based on the data flowing through. A parallel state runs multiple branches at the same time. And a map state iterates over a collection, one item at a time. There are a few supporting states too. Wait, pass, succeed, and fail. But task, choice, parallel, and map are the ones that shape almost every workflow you'll design. Here's the part that makes step functions genuinely powerful. And notice there's no application code doing it. This is a task state that processes a payment. The read block says if it fails, wait 2 seconds, try again, back off exponentially, up to 3 attempts. The catch block says if all those retries are exhausted, don't crash. Transition to a cancel order step instead. That's the compensating action that undoes the order cleanly. All of this lives in the workflow definition in JSON. You didn't write a single try except line, and every future step inherits the same reliable pattern. A task state can call a service in 3 different ways, and the pattern you choose matters. Request response is the simplest. Call the API and move straight to the next state. The .sync pattern calls the service and waits for it to finish, which is what you want for something like an ECS task or a long glue job. And the wait for task token pattern pauses the whole workflow until an external system or a human sends back a token. Important qualifier here, .sync and wait for task token are standard workflow patterns only. Express workflows support request response exclusively. Underneath all of this, through SDK integrations, a single task can reach over 9,000 API actions across more than 200 Amazon Web Services, which means many workflows need no Lambda glue at all. That wait for task token pattern is easiest to picture as a dry cleaner claim ticket. You drop off your suit and get a ticket. The cleaner doesn't call you every 5 minutes asking if you're ready. The job just waits. When you come back and hand over the ticket, the process resumes. Step functions works the same way. It issues a token, pauses without burning any cost polling, and only continues when someone returns that token. That's the canonical pattern for a human approval step in the middle of a workflow. Just keep in mind this callback pattern requires a standard workflow. Express workflows only support the fire and forget request response pattern. Now let's put it together as MegaCorp's order workflow. It starts by validating inventory. Then, a choice state asks, is the item in stock? If it is, we move to process payment, the step with 3 retries and a catch that cancels the order if payment ultimately fails. Once payment succeeds, a parallel state fires 2 branches at the same time. Update inventory and send a confirmation email, running simultaneously. And when both finish, the workflow triggers fulfillment. That's 5 coordinated steps with retries and branching, and none of that coordination lives in your application code. Here's a detail about that parallel state that catches people. If any single branch fails, the entire parallel state fails, and every other branch is stopped immediately. So in MegaCorp's workflow, if sending the email fails, the inventory update stops too, even though they're unrelated. The fix is to put your catch at the parallel state level, so you handle the failure gracefully instead of letting one broken branch take down the rest. Designed for that, and the parallel path stays reliable. Quick recap on the orchestrator. Step Functions replaces those hand-coded Lambda chains with a visual state machine. You build the workflow from task, choice, parallel, and map states. Retry and catch stored in the workflow definition, not scattered through your application code. And remember the parallel behavior. One branch failing stops the whole parallel state, so catch at that level. Next, we look at the one decision within Step Functions that trips people up the most. Standard versus Express. There are 2 workflow types, and the cleanest way to feel the difference is cargo ship versus speedboat. A standard workflow is the cargo ship. It carries heavy loads on long voyages, keeps a meticulous manifest of everything on board, and costs more per unit. An express workflow is the speedboat, extremely fast, extremely high volume, much cheaper per trip, but it doesn't keep detailed records by default. That trade-off, durability and audit versus speed and cost, is the whole decision. Here they are, side by side. A standard workflow runs up to a full year, gives you exactly once execution, keeps 90 days of history right in the console, handles around 2,000 starts per second, and is billed per state transition, $25 per million. An express workflow runs up to 5 minutes. Uses at least on semantics when it's asynchronous, keeps history only in CloudWatch logs, and scales to 100,000 transitions per second. The billing model here has 3 dimensions: executions, duration billed in 100 millisecond increments, and memory consumed. For any workflow that runs more than a fraction of a second, the duration and memory charges will dominate. Long, audible, and exactly once on the left. Fast, high volume, and duration priced on the right. Amazon Web Services draws the line clearly in its own docs. Standard workflows follow an exactly once model. Your tasks never run more than once, unless you asked for a retry. Express workflows use an at least once model, which makes them ideal for idempotent actions like transforming input and storing it in DynamoDB with a put. That single phrase, exactly once versus at least once, is the heart of the whole decision. Charge a card under at least once, and you risk billing someone twice. Here's the decision rule you can carry into any scenario. If you'd be upset when it runs twice, use standard, payments, order creation, anything irreversible. If the operation is idempotent and high volume, think streaming data, IoT telemetry, a DynamoDB put that's safe to repeat, use Express. That's it. Ask yourself the one scenario. Would running this twice cause harm? Yes means standard. No means Express is on the table. Look at what volume does to the bill. At 10 million events, standard runs about $250 because you pay per state transition. Express, at the same 10 million, starts at around $10 in execution fees alone. That's the gap between $25 per million transitions and $1 per million executions. Keep in mind that figure covers execution charges only. For Express, duration and memory costs stack on top and will dominate for any workflow that runs longer than a fraction of a second. But for very short, high volume, idempotent work, Express wins on cost, and it isn't close. 2 things about Express catch teams in production. First, the workflow type is immutable. You can't switch a state machine from standard to express later. Pick wrong, and you rebuild it from scratch, so choose deliberately up front. Second, Express keeps no execution history in the console. You must enable CloudWatch logging when you create it, or you lose all observability into failed runs. Remember, asynchronous Express is at least once, so never use it for payments or order creation. And one useful variant, Synchronous Express, returns the result directly through the start sync execution call, which we'll use in a moment. Now let's slot these two into the full picture with the 3 services from last episode. Each one owns a distinct keyword. API Gateway is exposed as Serverless API. Step Functions is sequence steps with retries. SQS is point-to-point buffering between one producer and one consumer. S and S is fan out to many subscribers at once. And EventBridge is content-based routing from many sources. 5 services, 5 jobs. This scenario almost always hands you the keyword, and that one word picks the service. Let's apply that rule to MegaCorp end-to-end. Orders come in over HTTP, so the intake is API Gateway. Once an order lands, we need to validate, pay, and fulfill with retries. That's step functions orchestrating the workflow. When the order's done, and we need to notify several partner systems at the same moment, that's SNS, fanning out, and routing report events by their content from many different sources is EventBridge. One architecture, 4 services, each chosen by its keyword. That's exactly how these scenario questions want you to reason. Here's the mental model to carry out of this episode. Picture a restaurant. API Gateway is the host. It greets customers, checks the reservation, and seats them at the right table. Lambda is the line cook who actually prepares the dish. And Step Functions is the kitchen manager who coordinates the complex orders, telling the grill and the salad station to work in parallel and retrying when something goes wrong. Simple orders go straight from host to cook. Complex ones bring in the manager. And there are no servers to run at any layer. There's one timeout that shapes a lot of designs. API Gateway has a default maximum integration timeout of 29 seconds. For HTTP APIs and edge-optimized REST APIs, that ceiling is fixed. You cannot raise it. For regional REST APIs and private REST APIs, Amazon Web Services added a quota increase option in June 2024, so you can request a higher limit, though doing so reduces your account-level throttle quota. In practice, leaning on a longer timeout is still not the recommended pattern for workflows that take minutes. The cleaner fix is to go asynchronous. Start the step functions execution, then immediately return 22 accepted to the caller. The workflow keeps running in the background, and the client either pulls for the result or receives a callback when it finishes. Anytime a workflow runs long, that's the pattern to reach for. So how do you get a result back through the gateway? There are 2 patterns. A REST. A PI calling start execution is always asynchronous. It hands you back an execution reference, not the results, and the client has to pull describe execution to find out what happened. That's your choice for long-running workflows. But if you need the answer right now, an HTTP API calling start sync execution against a synchronous express workflow waits for completion and returns the result directly, with no Lambda in the middle. Fast, synchronous, truly serverless orchestration at the HTTP layer. Let's carry these rules forward. Expose a serverless API points to API Gateway. Coordinate a multi-step workflow with retries points to step functions. Reach for the REST API when you need usage plans, keys, WAF, or caching, and the HTTP API when you just want cheap, simple proxying. Non-idempotent work goes to standard for exactly once. Idempotent high-volume work goes to express. Anything over 29 seconds means go async, 22 accepted, then pull or callback. And API keys identify and throttle, they never authenticate. Now let's see how well you absorbed all of this with a quick 5-question quiz. All right, time to put your knowledge to the test. Question 1. A retailer needs a public HTTP endpoint in front of a Lambda function. It must enforce per-client throttling, issue API keys to identify partners, and integrate with Amazon Web Services WAF. Which choice fits? Is it A, an API gateway REST, API? B, an API gateway, HTTP API? C, a Step Functions Express workflow? Or D, EventBridge with content-based rules? Think about which product carries those 3 features. The right call here is A, the REST API. Per client throttling, usage plans with API keys, and WAF integration are all REST API features. The HTTP API is cheaper and simpler, but it supports none of them. Question 2. An order processing workflow charges a customer's credit card as 1 step, and that card must never be charged more than once. Which workflow type is appropriate? A, express, because payments are high volume. B, either type, since retries prevent duplicates. C, standard, because it provides exactly once execution. Or D, synchronous express for the immediate response. Lock in your answer before I give it away. This one is C, the standard workflow. Charging a card is non-idempotent, so it demands exactly once execution. Only standard guarantees that. Asynchronous express uses at least once semantics and could run that charge step twice. Question 3. A workflow triggered through API gateway takes about 90 seconds to finish, and users are getting 504 gateway timeout errors. What's the correct fix? A, increase the Lambda timeout to 120 seconds. B, enable response caching. C, switch the REST API to an HTTP API to raise the limit. Or D, return 22 accepted right after start execution and let the client pull or get a callback. Think about where that timeout actually lives. If you said D, well done. API Gateway's default 29-second integration timeout cannot be raised for HTTP APIs or edge-optimized REST APIs. Raising a Lambda timeout does nothing about a gateway timeout. The answer is to go async, start the workflow, return 22 accepted immediately, then pull or use a callback. Question 4. A team secures their API by giving each caller an API key and relying on it to control access. A security review flags this. Why? A, PI keys expire too quickly. B, API keys identify clients and enforce throttling, but do not authenticate or authorize callers. C, API keys only work with HTTP APIs. Or D, API keys need a Lambda authorizer to work at all. Run the decision rule from earlier before you answer. It has to be B, and here's why. Amazon Web Services explicitly warns against using API keys for authentication or authorization. They identify clients and enforce throttle and quota limits only. Real access control needs IAM, a Cognito user pool, or a Lambda authorizer. Let's test a concept from an earlier episode. Question 5. A design needs to fan out one published message to several independent subscribers at the same time, each processing its own copy. Which service fits? A, SQS for point-to-point buffering. B, Step Functions to sequence the subscribers. C, SNS for fan out to many subscribers. Or D, API gateway is the front door. Got your pick? Let's see. The answer is C, Amazon SNS. Delivering an identical copy of one message to many subscribers at once is the fan-out pattern, and that's SNS. SQS is point-to-point buffering, step function sequences steps, and API gateway is the HTTP front door. That's application integration, API gateway, and step functions in the bag. If this is making your prep easier, please subscribe. It's the simplest way to support the channel and spread these to new students. Tell me in the comments what clicked. Got an exam you want next? Request it below. I follow those. And any feedback on the pace or the style? Send it my way. See you in the next one.